to talk about right now is the logic behind the statistics we use in experiments. Okay, so for example, in class the other day, we did a memory experiment. So half the class was giving one set of instructions about visualizing and feelings on words. The other was saying, listen for the letter E. And between those two groups, we got different numbers of words remembered. And the average was about 6 words versus 8 words between the two groups, a 2-word difference. Now, I handed out the actual data set. And if we look at the data for either group, so let's just look at group 1, there are all these scores. They were given the same instructions, but they have very different scores. I mean, there are a whole bunch of 5s, there's a 10, a 3, a 7. So the first question is, why are those scores different? If they were asked to do the same, why didn't they remember exactly the same number of words? Well, of course, there's a lot of reasons, right? People have different memory abilities. They may have been more or less tired or paying more attention. Some people had an exam afterwards, so they weren't really focused. Some people are just kind of like, oh, what a dumb demo, and they're not really trying very hard. Some people might have understood the directions differently. So all of these reasons make their memory, their data they gave us, different. And this is random error. Now, these are specifically individual differences. And I want you to remember that the biggest source of random error in your data set is going to be from individual differences. The fact that you have different people serving as participants, and they just bring their own abilities and motivations to doing your task. Okay. Now, for the statistics, what we want to know is if I have two groups and they have different average number of words remembered, different average for the dependent variable, I want to know, well, is that because the independent variable made these groups different? Or is it just simply because they're different people? I mean, if I grab 20 people and measure something about them, and I grab another 20 people, and I don't do anything different, I just measure the same thing, I'm not going to get the exact same average. I'm not going to say, oh, again, it's 6.2 words remembered. I would be really shocked if that happened. Now, if my independent variable is the one reason that these two groups are different, 6 words versus 8 words, I need to know that. Now, if they were so different, like my independent variable made this group remember like 2 words on average, and this group remember 17 words on average, that would be this huge difference, and I'd be like, wow, I hardly have to run the statistics to know that. But it's rarely like that, right? And so the 6 versus 8, we don't know if that's different until we run the stats. Now, what the stats that we're thinking of are going to do, things like a t-test or an ANOVA, is they're going to look at 2 sources of variability. Variability or variance is differences in scores. So I'm going to write up some possible curves for these data sets. So let's say here's group 1, and here's group 2, and there's my 6.2 word difference and my 8.3 word difference, something like that. The first thing a t-test is going to look at is, well, what is the difference between the means? T-tests and ANOVAs are, they test for the difference between averages, group averages. So I'm looking right here between the means of these two groups. How big is it? That's my between group difference. It's one measure of how my groups are different. Group 1 had a mean of 6.2, group 2 had a mean of 8.3. So between group difference. So I'm going to write T, or the T-score, equals, and this isn't the calculation, but it's just telling you conceptually what it looks at. So on the top of my fraction here, I'm going to put between group variance. Okay, between group variance. And it's going to compare that spread between my 2 scores with how much variability do I have simply within my groups, right? Group 1, the graph is this wide. Group 2, it's this wide. That's from all those individual differences. And you can see there's a lot of overlap in these 2 things, these 2 groups. And so I'm not really sure if they represent truly 2 distinct populations, one of which remembers more words than the other, or if this is simply sampling error. I got 20 people in one group, 20 in the other. They're going to give me slightly different data. This is just sampling error. I mean, imagine if the situation instead was this. I'm going to draw 2 curves with the exact same means, but very different standard deviation. So So here I've kept the between group difference the same. The spread between the two curves is the same. But look how skinny these are. I made much smaller within group variability, much smaller, okay? And when they don't overlap, I'm feeling confident that these represent two different populations. Here, where there's a ton of overlap, I'm just not so sure. So back to what the t-score does, it puts some measure of between group variability on top. And it's going to divide that with a measure of within group variability. How wide are these curves? So I'm going to put within group variance on the bottom. Now, when I run statistics, and it's going to pop out a t-score, I want a big t-score because that's going to be significant. So, let's see. If I want to do division and end up with a big number, well, I'm going to want a big number on top. I want these curves to be as far apart as they can get. You know, I just want the IV to really have an impact and push them apart. So I'm hoping that the top number is big, the between group variance is big. So I'm going to write big and then put a smiley face. That would make me happy. Now, if I'm going to do division and I want to end up with a big number down here, I'm going to want a little number on the bottom. I want those curves to be small, each individual curve to be skinny, not a whole lot of variability within the group. I want it all to be between group. So I'm going to put the word small with a smiley face over here. Oh, gotta make them smile. So if a big number divided by a small number, I'm going to end up with a big number. So I want my t-score to be big. Now actually, when t-scores get spit out, like a t-score of 8 or 12 or 27, that number doesn't actually mean anything to me. I don't know how big is big enough, but with every statistic that we run, the computer, or SPSS, is going to spit out the statistic, the t-score, or for ANOVAs, that's analysis of variance, it's an F-score, or even a correlation or a chi-score, all these things. It also pops out a p-value. And what I know about t-scores is the bigger the t-score, the smaller the p-value. And that I want. I want small p-values, and we're going to talk about that in a minute. So if a t-score is big, my p-value is going to be small. And of course, you've probably heard, I want p-value to be less than 0.05. That's just this sort of cutoff that we've all agreed, oh yeah, that's good enough. So p-values that are smaller than 0.05 make me happy as a researcher. So I'm just going to write p less than 0.05. Okay. Now again, I have the t-score up here, but for ANOVA, which is an acronym for analysis of variance, it spits out an F-score, and it's using the same ideas, although it calculates itself differently. So I want you to know t-scores, F-scores, they should be big. That will make your p-value small, which is great. We're going to do a different video to talk about p-values and rejecting null hypotheses and stuff, so you need to check those out. Also, between the t and the ANOVA, what I want you to know is t-scores you can use when you have 2 groups, but if you have 3 or more groups, then you have to use the ANOVA. Okay, so that's just how that works.